Okay, the key to all of this chemistry lies in the behavior of water. You may have been told that water is neutral, neither acid nor base, neither acidic nor basic. And that's fine, it got you to a certain point. The actual answer is it's a little bit more complicated than that. Water is something that we call amphoteric or amphiprotic, as it appears that this word is now morphing into. It used to always be called amphoteric, which means it can do both things. And now amphiprotic means a little bit more specific. So water is amphoteric. It acts like an acid when you put it in the presence of base. And it acts like a base when you put it in the presence of acid. So it really kind of rides the fence. And if you just leave it on its own, it does something without any external help. It splits apart into H+, the hydronium ion, and OH-, the hydroxide ion. Now there is a reason why the plus charge is on the right-hand side of this and the negative charge is on the left-hand side. For many, many years, it seemed to be normal to call hydroxide OH-. Now the minus belongs to this, to the OH. But it turns out that the minus is seated on the oxygen. And so over the course of time, that negative has moved from being a trailing superscripted negative to being out in front. For the purposes of making clear that it belongs to the oxygen and that it's not, this is not an oxygen with an H and then the H has a negative on it. The negative is never on the hydrogen, it's always on the oxygen. Okay, so this splits apart into being an acid and an equal and opposite number of bases. And that reaction is in equilibrium. And that equilibrium lies very, very far to the left on the reactant side. But K for this reaction. Let's write what K is. So this is one way of writing that. I'm going to show you another, and then I'm going to show you why there is no difference and why we're going to continue with this. Because there is a school of thought. They actually don't write it down at all in the book. It's not there at all. It's on page, supposedly, page 676. Here is autoionization of water. And they get to the next place that I'm going to start looking at, the K for this, the equilibrium constant. But they don't write what comes next, or where it comes from. I'm going to show you two ways. This is my personal way of writing it, because mathematically it works and it's simple. You have an acid and base, you get a water, and they split apart. There is a school of thought that says, yeah, it doesn't really go like that, that all these charges in solution have to be solvated. Solvated. So there's a school of thought that says you take an H2O and an H2O, and you add H plus to one of them. And so you get this, the H3O plus ion. And that has satisfied some people, some very, very vocal people, that say, I can live with this. I like this description of an acid a little bit better than that description, because this one doesn't, this one just shows me H plus is floating around the solution, and I don't think that's a true representation. Do you remember solvation spheres? Day one. An H plus is likely not to be solvated by one water molecule, but this is showing. Oops. How many am I up to? 1, 2, 3, 4, 5. That's not nearly enough. There you go. That's a truer representation. And H plus is likely solvated by 11 water molecules. So the people that say, you can't have that, it's not a true representation of what's going on inside the solution, are somehow okay with this. What it really should be, but nobody's prepared to write H23O11 plus down. Okay. So this actually is gonna kind of screw some of the math up later down the line. This is not a complete representation of what's going on, but it's simpler and it works. This is a step in the direction of saying ions in solution are solvated. Therefore, one of these water molecules splits apart, the other one solvates it. I'm not a fan. This is a liquid. This is in solution, and that's in solution. This would be a liquid, and that would be a liquid, and this would be in solution, and this would be in solution. What we're doing right now is heading to the point that says it doesn't matter. Okay, for this description, my first one, the simple one. How do you write the K expression? Concentration of the products divided by the concentration of the reactants, which equals. Look at what your products are. Put them in boxes. Write them on the right-hand side of the equal sign. Then look at what your reactants are. Put them in boxes. And write them underneath. There's only one H plus and one OH minus, so there's no raising to any powers here. And then underneath it, there's my H2O. Wait a minute. We need that red pen. What do I have to do? That's in aqueous solution. It has a concentration. That's in aqueous solution. It has a concentration. That's a liquid. Liquids don't have concentrations. Take it off. Oh, look, my negative moved to the end. I wonder how they're doing it in the book. Yeah, the book has it trailing as well. So I think that when you see me write this down, I'm going to show it both ways. That some of the time, if I'm writing this out as a fragment that's doing something, doing some reaction, I'm going to settle that negative right here on the oxygen. I teach a lot of organic chemistry, and so I show where the reaction comes from, and I show where the reaction goes to. Okay, so I'm going to settle that charge where it actually belongs. In a mathematical formula, just as long as it's inside the box, I think we're okay. So force a habit right there, put it back where it used to be, and it's that way in the book too. That's my value of K. And that's the value that K does all on its own. So it gets a subscript. This is now KW. When you take a number and you divide it by another number, like we did yesterday in a fraction, the fancy word for that fraction is quotient. And we found a value Q, and we mapped to see if it was close to K. So quotient is a number divided by another number. What are two numbers multiplied by each other called? That's the product. So this has become known, KW has become known as the ion product, because it's just two numbers multiplied by each other. There is no denominator. There's nothing dividing in because the liquid goes away. Okay? This is now called the ion product for water. And it has a value that is 1 I don't think I'm going to bother. I don't think I'm going to put a decimal in it. I think it's just, let's see how the book does it. The book has the first 0. Times 10 to the negative 14. So we're going to see ion product come up in this chapter specifically for Kw. And then in the next chapter, we're going to look at solubility of salts. And they also have an ion product. They have no number that divides into them. Different set of circumstances lead to the same thing. Okay? 10 to the negative 14. Where on my equilibrium is 10 to the negative 14? Right side or left side? How far to the left? Yeah. Only a tiny amount. So if we have a beaker of pure water, a tiny amount of it has split apart to make acid and base. But there's an even number, there's an equal number of acid and base in that solution. So when we go looking to see, can we find acid? We don't find it. Because the number of base, the concentration of base is equal to it. So our solution is not acidic. Yes, there's acid floating around, but there's also base floating around at the same time. It evens out. All right, let's do it for this. The description that I'm not so fond of. K here is H3O plus OH minus over H2O squared. I got 2 of them. But they're both liquids, so they can both go away. And you still end up with the same thing. The Kw under a different description is H3O plus OH minus. Okay? There are reasons why I use this one and not that one. But if you have learned this in high school a different way, those of you who are retaking and took this with a different professor who had previously done H3O plus, and you're happy with that, keep doing it. Okay. My personal preference for this is not going to be reflected in your grade at all. If you write that instead of this, they're both valid. If you are going back to your own host institution and they do H3O plus instead of H plus, and you know that, you should probably not dig yourself into a bad habit, because some people are picky about this. I had a very dear friend of mine, analytical chemist professor, who insisted it be H3O plus. Wouldn't listen to my argument that he was wrong. Not only is it wrong, but it screws up the math further down the line. Further down the line, it's going to complicate the math in a way that we're not going to concern ourselves with. Okay. All right. So if that reaction can go forwards, can go backwards. Let's look at that back reaction just for a second, and can we see what our definition of an acid is? Just look at this in reverse. There you go. So I've isolated this now. So I've put the negative back on the oxygen. Now look at that reverse reaction. I'm going to write it out, and then I'm going to draw the Lewis structures. Acid plus base makes water. Now we know that that equilibrium lives way, way, way over to the left-hand side of the way that it was previously written. So this reaction is going to be facile, easy, coming this way. Okay? Let's explore what this actually means. Here's a hydrogen. If it were a hydrogen atom, you would have one electron. There's a hydrogen atom. There's a Lewis structure. Don't know if you want dots. Doesn't matter whether the dots are X's or smiley faces. It really, something symbolic that I can count. Okay? There is an H dot. That is a hydrogen atom. It is now a hydrogen ion because I have removed the electron. Here is an oxygen. How many electrons does oxygen have in its valency? Group 6. 1, 2, 3, 4. So you should have learned to write them top counterclockwise, keeping them as far apart from each other as you can, symbolically. This molecule's in 3 dimensions, not in 2. And then when you have to pair them up, go ahead and pair them up. So oxygen has 2 bonding electrons and 2 non-bonding pairs of electrons. Okay. It also has a bond to hydrogen. So this would be OH. That's an oxygen with a hydrogen bonded to it. That is a 7-electron species. 7 electrons is not 8. There's no such thing as a 7-electron rule. It's an 8-electron rule. I need 8 electrons to make this thing comfortable. Guess where it got the extra electron from? Came from something out of group 1. Okay, so now this has 8 electrons and a negative charge. That negative charge comes from that one right there. That electron is the odd electron out. It does not belong to the oxygen, and it does not belong to the hydrogen that is in the bond. It is an external, unshared electron. Okay. I'm going to take these 2 electrons. Motion of 2 electrons in chemistry is depicted by a curved arrow that has a double barbed arrowhead. I'm going to take those 2 electrons and donate them to the hydrogen. And that makes water. So a covalent bond is 2 electrons shared between 2 atoms. And in the simple case, when you start teaching this out of the book, it's an electron from this atom and an electron from that atom. And they come together and they share those two electrons between these two atoms, and you make a covalent bond. But all the definition of a covalent bond is two electrons shared between two atoms. So we could do it this way. You have two electrons here that I'm not using for anything right now, and no electrons here. And I donate both of them. I've got two electrons shared between two atoms. So I can do it this way, 1 and 1, or I can do 2 and none. I still end up with a covalent bond. And after you scramble this around for a second, can you tell which electron belonged anywhere? No. Can't tell now. So that becomes what we call a dative bond, or now called a coordinate covalent bond. So this becomes a coordinate covalent bond. That is two electrons shared between two atoms, but both of the electrons started life on one of the atoms. Okay. What were our definitions of an acid and a base? Arrhenius. What does Arrhenius say?
Changes the concentration.
Anything that puts H plus into solution is an Arrhenius acid. And Lowry and Bronsted say an acid is a proton donor. It's going to put that H plus to use. It's going to donate it to something else. And then Lewis says that an acid is an electron pair acceptor. It's on the board, right there. Here's the acid. What does the acid do? It's accepting that pair of electrons. Okay. Lewis saw this behavior in molecules where this was not a hydrogen. It's possible. Boron can do this. A molecule like BF3 only has 6 valence electrons. It would love to have 8 valence electrons. It can do it if it accepts a pair of electrons from something else. BF3 doesn't have any hydrogen. It cannot put H plus into solution, but it can accept a pair of electrons, and in accepting them, that's acidic behavior. Okay. Now, the trouble with general chemistry is it dwells far too much on the acid and doesn't pay nearly enough attention to the base. And when you get to do organic chemistry, which is the next full year after this, we're going to be talking about the bases pretty much exclusively, because they're the things that cause the reactions to occur. This is a base. It is an electron pair donor. That's the base. Here's the acid. It is an electron pair acceptor. Okay. AC, acceptor, acid. Okay, so we have a number for this. That's our first key into quantifying acid-base behavior. Kw has a value that is 10 to the negative 14. Okay. If H2O takes H plus and no H minus, and Kw is H plus times OH minus, which equals 1 times 10 to the negative 14. We talked about exponents last week. I think we talked about them last week. And how, probably when we were doing Arrhenius, and how they interact with each other. So if the product of those two numbers, the concentration of H plus and the concentration of OH minus, is 1 times 10 to the negative 14, how much H plus does water put into solution naturally, just on its own, without anybody asking it to do it? This is a number that you can do in your head.
1 times 10 to the negative 7.
That value is 1 times 10 to the negative 7. What? Moles per liter. What is the other number? Okay. Because those numbers have to be the same as each other. Where did the H plus come from? It came from an H2O. So this is AB breaking apart to make some A and some B. There's no way that if I have 100 ABs in solution and I break apart 25 of them, I get 25 A's. How many B's do I make? 25. It has to be the same number. This is a dissociation. Therefore, whatever number this is, that number has to be the same number. And when exponents multiply, you add the exponents together to get this number to equal that number. What you just do right here. When you multiply two numbers that are exponents, you just add the exponents. So 1 times 10 to the 3 times 1 times 10 to the 14 equals 1 times 10 to the 17. 1 times 10 to the 9 times 2 times 10 to the 8 equals. Don't need your calculator. These are huge numbers, but the 1 and the 2 multiply. The numbers before the exponents actually multiply because you're telling it to do it, but then the exponents add. And 9 and 8, 17. The exponents add. Okay, so my number came out, and I find that number experimentally, this number, 1 times 10 to the negative 14. That's my ion product for ionization of water. Which means those numbers have to be 1 times 10 to the negative 7 each. Okay. So let's think. Therefore, the H plus concentration in pure water is 1 times 10 to the negative 7 moles per liter. If I know this number, I automatically know the concentration of base, because they must balance. All right, I'm going to, so I have a value, like 1 times 10 to the negative 14 is 0.0. That number is uncomfortably small. I don't like it. So the number that I'm going to find for my concentration of ion in solution is somewhere between this small and somewhere between like, that small. Again, a number that I'm not comfortable with, that is too small. My calculator only has 8 digits. I can't get down that far. I don't know how to use the exponent function on my calculator. So I type things in at 0.000, I've run out of space. This is uncomfortably small for me. And when the range of numbers that we have to deal with is outside of our comfort zone, what do we do to the underlying numbers? We take the log of it. And the log turns big ranges of numbers into small, manageable, understandable numbers. Now, there is a mathematical function, and that mathematical function is called P. And the P of a number is the negative. Our numbers are less than 0. The log of any number that is less than 0 has a negative value. So the negative right here that goes in front of the log is to turn a negative number back into being a positive number. P means negative log to the base 10, not the natural log, the log to the base 10. So PH now becomes the negative log of my H plus hydronium ion concentration, and we are treating all H pluses as the true acid that's actually floating around the solution. So this gives me a quantity for my acid. So if that is the negative log to the base 10 of 1.0 times 10 to the negative 7, use your calculator. 7. So the log of 1 times 10 to the negative 7 is negative 7. And then the negative in front of the log puts this to be a positive number, because we don't like negative numbers either. There are people out in the world that you will talk to, regular folk, that do not want to hear about negative numbers. So the pH of pure water is 7. We're going to have a sliding scale. And the scale goes from 0 through 17, through 7, out to 14. And everything that is below 7 is considered acidic. And everything that is above 7 is considered basic. And our strong acids live way down here. Last week in lab, those of you that are in lab took a dilute amount of a strong acid and found that its pH was about 2. And then we added some dilute weak acid, acetic acid, and found that its pH was somewhere in the 4s. So weak acids are somewhere here. Your perchloric acid's going to be almost 0. Your sulfuric acid's going to be very, very low numbers. And then we're going to start inching up into the hydrochlorics and the phosphorics of the world. Still going to be low numbers. Strong bases go here. We haven't seen examples, named examples of strong and weak bases yet. It's all on our radar. It's going to show up. Okay, this is crying out for a calculation. And we can do calculations one of 2 ways. Because Kw tells me that the H plus concentration times the OH minus concentration equals 1 times 10 to the negative 14. pH takes one of those numbers, which is 1 times 10 to the negative 7, and turns it into a usable number that turned out to be 7. If I did the same mathematical function for the OH, I would also turn it 1.0 times 10 to the negative 7 into a 7. So pH plus pOH now equals 14. Okay? So if I give you one of those numbers, or one of these numbers, you can find all the other missing numbers. If I tell you pH, you can immediately find pOH, and from that you can find the concentration of hydroxide, and from that you could find the H plus concentration. We can find any one of all of these numbers missing from just one piece of information. Yeah.
Do you need to use your calculator at all, or is it just the positive version of the exponent?
Pretty much, but they're not always going to be 1.0.
Okay. Like let's say, what if it was 2.0? What would you
Yeah, use your calculator.
How would you?
Yeah. Not in my head. I'd need a logbook or a calculator. Okay, so let's do some questions. Here we go. We can do this either way. A sodium hydroxide solution. We haven't talked about hydroxides yet, other than they're the other side of my ion product. A sodium solution, sodium hydroxide solution is found to have hydroxide concentration that is equal to 2.9 times 10 to the negative 4 moles per liter. Find the pH of the solution. Okay? We can do this 2 ways. First, I know that Kw is H plus times minus, which is equal to 1 times 10 to the negative 14. Okay. I now have two of the numbers that I need to complete this transaction. I got this number, and I've got that number. I'm being asked to find ultimately H plus. So what I can do is I can see that the H plus would be equal to that. So I'm going to isolate the H plus, leave it where it is on this left-hand side of the equal sign, move the hydroxide concentration across the equal sign where it drops to be a denominator, and now put your numbers in. So that's 1 times 10 to the negative 14 divided by 2.9 times 10 to the negative 9. Those numbers, do I have a number for that? No. I have not worked it out. Although I do have an answer. Yeah. Do we have a number? That's going to give you a number. Have we figured out what the number is? Not yet.
It's 2.9 times 10 to the negative fourth, right?
Oh,
Or is
that's a
it-
4.
Or is it 9?
The light was shining, that's 4. I should check my question. It is a 4. Yeah. You stand right here, the light was shining right on it. It made me. Thank you.
So 3.4 times 10 to the negative 11.
Okay. 3.4 times 10 to the negative 11. Rule of thumb, it's going to give you a ballpark right here. If you divide an exponent by another exponent, you subtract this number from that number. So my answer should have come out somewhere around 10 to the negative 10. And it did. But of course, I've got to divide a small number by a bigger number, which knocks it back a digit. Okay? All right, that is H plus. It's not what the question was asking, but I'm getting close to it. The question is asking for pH, which is negative log to the base 10 of that H plus concentration, which is negative log to the 10 of my 3.4 times 10 to the 11, which equals, so throw that into a log. It'll come out as a negative number and you just flip the number. Okay. Yeah, so we're kind of stuck that we have two significant figures. And your calculator is going to tell you 10.456 or something like that. And we don't have that. 10.5 we can live with. What are my units for pH? Doesn't have any. Doesn't have units. Okay. That's one way. Let's do a different one. For my money, this way is quicker and doesn't go through the big ugly numbers. Goes directly to the nice, easy to understand numbers. In the question, you were given hydroxide concentration, which was 2.9 times 10 to the negative 4. So the first thing that I'm going to do is find POH. That is negative to the log, negative, log to the base 10 of my OH concentration, which is negative log to the base 10 of 2.9 times 10 to the negative 4, which equals say it.
3.54.
Mm-hmm. 3.5. Okay. Next logic. pH plus POH equals 14. Therefore, pH is 14 minus POH. Just moving it across the equal sign. Yeah? Which is 14 minus 3.5 equals 10.5. Same answer. This one feels simpler. You go immediately into the easy to understand number. You don't dwell on, oh, I've got to divide two exponents. This one looks more complicated. That one feels easier. They're both the same as each other. Okay, there's no real difference. Okay, does that make sense? Sure. The solution has a hydroxide concentration that is larger than the neutral value that hydroxide should be. A neutral value of hydroxide would be 1 times 10 to the negative 7. So this solution has 1,000 times more than what my neutral should be. 10 to the negative 7, roll back to 10 to the negative 5, 10 to the negative 6, no, what am I saying, 7, then 6, then 5, then 4. That's 3 zeros. That's 1,000 times. So this is 1,000 times more basic than a neutral solution. So it should put me somewhere here. I don't know exactly where, but it's going to be a number that's larger than 7. So that makes logical sense. Okay? All right, we'll come back tomorrow and we're going to start having the acids and the bases fight to the death. And we're going to realize that strong acids and strong bases kill each other all outright. Everybody dies. But in the battle between a strong acid and a weak base, or a weak acid and a strong base, somebody survives. And we can map the pH of the final solution, which is curiously what you did in lab on Thursday. Okay? See you tomorrow. Or this afternoon, depending on if you're in lab. Did you sign up for the lab as well?
Yes.
Okay.
How do you do the log 10? I mean, the log base 10?